Okay, so this is going to be your Chapter 7 or Week 8 lecture, and this is all about attribute data. We talk about tables, and how our attributes are stored. Generally, that data comes in two basic types. An attribute table, which is a table that is associated with a feature, or a standalone table, like adding in just a table of Excel data that you're going to link to something. Tables have a pretty basic structure. It's no different than Excel or Access or any other database or spreadsheet that you would imagine. It's all about rows and columns, and a column is known as a field and a row is known as a record. One format that this data comes in is something called a flat file, and this stores data as rows of information in files, simple, robust, but it's not the best thing in the world for searching and querying stuff. Another is called a hierarchical database management system. So unlike a flat file, and I literally just drank coffee before I started this too, so don't give me any static in class about yawning during the videos. I'm literally recording this at 3 o'clock in the afternoon. Okay, so in a hierarchical table, there's this parent-child kind of relationship between different tables, and so different elements of information like billing history or service calls or what have you are nested all inside of other files and other folders, allowing you to, instead of search through all the database for the thing you're looking for, you can narrow it down to subsets and subsets and subsets until you want to do the search. And so from a structural standpoint, if you efficiently design the tables, how they're linked, it increases the proficiency that you can search and query information. Then there's relational geodatabases. These are highly flexible. They're ideal for open-ended applications where things get changed and added to. This is in general the type that we most often see in GIS applications. Okay, so let's talk about joining tables. Table joins allow two tables to be used as a single table. Basically, it takes table A and table B, and you start your join at one location. So I want to join data to, say, table A. Then you go to table A, and to that you're going to join table B. So then table A will look like this longer table with table B stuff with it. Multiple joins can be complicated. I recommend that if you're going to do something like this where you have to join a lot of different things, you want to join items individually to one set, not joining pairs of things together and then trying to join the join pairs, because that creates problems. Let's talk about some of the different kinds of joins. The most basic one is a simple one-to-one join where you've got two data sets and everything that's in one data set lines up neatly with one thing in the other data set. Many to one is a little bit different in this scenario, and now the verbiage can get a little bit confusing, and so I may not follow exactly along with what Price has in the text or what we see in the slides, because frankly the way that they list it I find confusing. So I'm going to try to explain it the best way I know how. So if you have a many-to-one cardinality, they say that means one record from the join table matches many records in the target table. To me, that's not a many-to-one, that's a one-to-many. I'm joining data from one record to many records. They look at it like you're joining many records to a single record. Anyway, what matters is, if you're joining one thing, like state information, to multiple other things like cities within a state, so that each city also has the state information, then that's very doable, because you're still only attaching one bit of information to every record in the data set that you're joining stuff to. Now, when you go the other direction, that creates a little bit more of a problem. In this example, you've got states data, and then you've got all these cities that exist in the state, and if you want to add up the population of all those cities and attach that to the state, maybe you want to, for example, calculate out the percent of the population of Washington state that exists in the major cities. So you've got a table of major cities, multiple ones, and you want to join it to that. Here's the problem. You can't attach multiple things to a single thing. That, in my mind, is what I would call a many to one. They're calling it a one to many. Here's the problem. If you're going to do this, you can't do it one to one, obviously. So it has to be a summarized join. Or you can use it to do a relate. Relates are similar, but not exactly the same thing as a join. Basically, a relate links up the data across the tables without joining them. And so it doesn't give you this one big table with everything that's all perfect in it. But with a relate, if for example you went to that target table and you selected the polygon Washington, in the attribute table from your join table, every record that had Washington as the state name, it would then select or highlight. And so it allows you to select something in one data set, and it then in turn selects multiple things in the other. So general rules of joining: everything's got to match everything one to one. So whatever you're bringing can only have you can, how to explain this without making it more confusing. If you're joining one thing to another thing, you can do that. If you're joining one thing to a bunch of things, you can do that. If you're joining a bunch of things to one thing, you can't do that without summarizing it or using a relate. Many to many is even more complicated. So let's go over these again. One to one, states to governors, countries to capitals, etc. I've already talked about my displeasure with the way that they label it, so I'm not going to really spend too much time going over it. Just know that there are multiple types of cardinalities: one to one, one to many, many to one, many to many. What happens when we don't have records to complete the joins? Well, you get a null value, and that's just it. It just means there's nothing there. How do you add a join? There's a tool for it. That's like the basic answer for everything in ArcGIS, anything, Pro, Desktop, whatever. How do you do that? There's a tool for it. Here you have multiple tables from different congresses, and you want to join them together. Select the input field, the two layers that you're joining, and it then keeps all the features. If there's a match, you get numbers, and if there's not, you get a null void, a value. Now sometimes it turns out we don't want to keep everything. Sometimes the nulls are important. Sometimes we want to create subsets. So for example, when we look at the statistics on this, we get this data set that shows us very irregular distribution. And the reason is because there's a whole lot of zero values. Now, maybe there is zero values, or maybe the zero values is an artifact of how the data is collected. In this case, a zero magnitude earthquake represents missing values, and that can really screw up the results for everything else. So maybe you only want to look at earthquakes that have a value greater than zero. Same way with charts. At some point in time, charts are great for exploring data. This is a scatter plot, and it shows the correlation between average temperature and latitude. But there are some areas where things don't quite want to line up exactly. And so you get some that are cold outliers or warm outliers, and you can select those on the graph, drawing a box around it. And interestingly enough, that should then light up everything in the attribute table as well. Summary statistics is just a basic tool that calculates all those fundamental types of statistics like mean, median, mode, standard deviation, etc. And basically you tell it what the input is, and then the field that you want to run the statistics on, what statistics you want, and the statistic types and all that kind of stuff, and it will then do exactly that. Now, statistics with a case field. This is kind of interesting. So you've got a whole bunch of statistics for all the cities in every state. But what you really want is these statistics calculated on a state-by-state basis. So how do you do that? Well, you select a case field. In this case, the case field they selected was state. And instead of calculating up those numbers for the entire data set, it then calculates those up based on that field. So what if the field you want doesn't exist and you can't join it in? Well, you can always make it. And so there's specific types of fields. You have to understand how that works a little bit before you go through it. But the main thing and the first thing is you have to define the field type. Once you do it, you can't change it. So you got to make sure you know that going in. And then when you name it, follow these rules. They're more than 13 characters, only numbers and letters, has to start with a letter. So binary data is one type format that you can deal with. And that's binary numbers is a base 2. Base 2 numbers are ones and zeros. Alright, so when we talk about bits, that's groups. Bits are grouped into sets of 8 that form a byte, and you can store up to 255 numbers. The more bytes that are added, the more larger numbers, the bigger the storage. And so without going through all this, I'm just going to go on to the next slide and talk a little bit about ASCII files. ASCII files are a text-based file that allows us to bring data in or take data out from various GIS setups. When we store stuff, if we want to have a text file that stores raster data or attribute data, an ASCII format is an easy way to do that. So let's talk about some of these byte storage limits. Again, I'm not going to quiz you on what is a byte or a bit or whatever, but what you need to know is if you're looking at a 1 byte data set, 255 values. That's 0 to or from 1 to 255. Alright, if you're looking at 2 bits, larger range, 3 bits more, 6 bits, etc. If you have signed numbers, it kind of makes it a little bit different. Integer versus float. Integers are whole real numbers. Floating point are basically scientific notation, and you have a set size for your mantissa, in other words, the number of decimals, unless you use a slightly different one, and then it doubles that. When we look at precision of floating point, your mantissa has 1, 2, 3, 4, 5, 6, 7 decimals. If you go to floating point, it doubles it, and it's called. Well, if you're in floating point, you go to double precision, it doubles it. It's database storage. Lots of different fields that you can define: ASCII versus binary, bytes, integers, and floats. These are the sort of things that you have to think about when you're trying to do stuff. For example, if you're in ASCII, you're limited to 10 bytes, and so Mississippi, you can't get the entire name of Mississippi in there. You have to be aware of those kind of things. If you're in a 2 byte binary, signed integers, plus or minus 32,767. Single precision floating point, it's a scientific notation based limit. So when we look at these different types, when you're going to create a field, which is what this really all boils down to, there's 6 basic field types: short and long for integers, float and double for decimals, and then there's text and date. So short and long, that just gives you numerical responses, but it has to be whole numbers, not decimals. There. Float and double are decimal value setups, and text is just text, and then dates are basically a structured numerical code. As far as the geometry, geodatabase attribute tables have special fields called shape underscore length and shape underscore area. The important thing to remember about these two are, if you're in a geodatabase, these fields are automatically updated. Now, what does that mean? It means if you dissolve, if you clip, if you cut, if you edit, if you change the projection, and you do anything that moves any of the lines, makes anything longer, anything shorter, anything bigger, anything smaller, it automatically updates the shape underscore length and shape underscore area fields and the attributes of those features. Now, all other fields that you might create that calculate or measure anything, you have to update those automatically, or I'm sorry, manually. They're not updated automatically. If we're talking about shape files, not features in a geodatabase, then guess what? There is no automatic updates. You have to, every time you change something, you need to update those geometric measurements. So how do we do all that? Well, bottom line is simple. If it's one of those two fields specifically in a geodatabase, you can assume it's correct. In every other instance, just go ahead and recalculate the values. That's the only way you'll know for sure. Coded domains are basically rules for what you can put into a database, and these actually can be pretty helpful. They eliminate putting in incorrect responses. They increase the speed that you can put things in, and in general are a good thing. Here's some examples. You can read through these at your leisure. I'm not going to sit here and read them off to you. How do you create domains? Again, you work through the tutorials in the chapter, and they'll go through this and tell you how to set it up, symbol types, coded values, etc. And then you can assign them. Schema. Schema is basically just this overarching design of how your database is set up. The structure of the table, that basically includes all the fields, what the definitions for everything is, the various domains. And so if you're going to do something, pretty tangible and extensive, you would want to know what your different fields are going to be, what your different domains are going to be, and all that kind of stuff. And so when you go about designing that and setting all that up, it's sort of the scheme behind how it works. That's called the schema. Table views, just to give you some idea, again, columns are fields, rows are records. You have little tabs there for the tables. The status bar at the bottom shows you whether you're looking at all the data or only the data that's selected. You've got various menus and table options and all kinds of stuff. So let's look at some more of the things that often come up. A lot of settings that we deal with primarily are there just to change how the tables are viewed and displayed. So from that standpoint, a lot of the settings are cosmetic, and they don't really change the table so much at its basis as they do just how we can visually interact with it. So some common things include aliases for field names that make them a lot more understandable, formatting for fields for things like consistent decimals or scientific figures, so that things get displayed correctly. Not displaying all the fields. It's quite a challenge because it's not something that comes up real often. You almost exclusively always forget to do this or how to do this. But you might have a data set that has a very, very, very large number of fields, and you might only be interested in 2 of them. And so the easiest thing to do is to turn off all the other fields in the properties so that the only thing that you see are the ones that you need. The data is still there, it's just not interrupting your analysis. So field views, that's kind of what I was just talking about in the previous one. And so you go through and you can make the switches from field views to data source mode, etc. It's critical to be aware of what types of changes are being made to fields when using the field view. In the data source view, renaming a field is permanent. So if you're in data source and you name something differently, it is a permanent change. There's the cosmetic, and there are the permanent changes that you can do. How do you edit them? You click the value box, type in the new values, and use the various tools there. Field calculating. It's a geoprocessing function. Can do an awful lot. So you can literally just look at the various helpers and mathematic functions and put in expressions and any number of things to calculate whatever it is that you want in the particular field that you're looking for. A lot of this runs off of code, and so you could, in theory, take in snippets of Python code and make a lot more complex calculations if you wanted to. Let's talk a little bit about importing data, specifically Excel data. There's a couple of limitations that you have to meet. Worksheets can be imported directly to Pro if they meet certain criteria. The first row has to contain legal field names. Every column has to contain one data type. And don't use things like NA or X to indicate missing values in a number column. There can't have any formulas or blank lines or merged cells. A dummy row may help the data type be determined correctly. Text, integers, floating points, etc. Comma delimited CSV files often work better. Text files have a lot of different formats: tab delimited, comma delimited, fixed column. Pro cannot read the fixed column format, but Excel can be used to convert a fixed column to a CSV.